Hello dear friends, I am Dr. Shailesh Palekar, working as an associate professor in the Department of Mechanical Engineering, Sanjeevani College of Engineering, Kopargaon. This is our fifth lecture for our second unit, that is forced vibrations of single degree of freedom systems, of our subject dynamics of machinery. In this lecture, we will see the forced vibrations due to support motion. Okay. Support motion. In case of locomotives or vehicles or any two-wheelers, wheels acts as a base or support for the system. The wheels can move vertically up and down on the road surface during the motion of the vehicle. Okay. At the same time, there is a relative motion between the wheels and the chassis. So, chassis is having motion relative to the wheels, and the wheels are having motion relative to the road surface. So, what is support motion is? As you know, in locomotives or in our two wheelers or four wheelers, the wheels acts as a base or support for the total system. On our wheels through chassis we have kept our total mass. Okay, but when these wheels move over the road surface because of the road irregularity or road bumps, we can say, these wheels again get exciting force, and they are giving the displacement to the body. And whatever the displacement we have to calculate, that displacement is might be summation, sometimes might be subtraction of the displacement given to the wheels. At the same time, we have to consider the displacement due to the engine which is provided to the chassis. So our chassis is suffering from the displacement from the engine side as well as the displacement from the wheel side also, means bottom, and that's what we can explain as support motion. So in case of locomotives, or we can say our vehicles, support means our road surface also provide the excitation to the system. So that we have to see here. Okay, in such cases what happens? There is a relative motion between the wheels and the chassis. So chassis is having motion relative to the wheels, and the wheels are having motion relative to the road surface. Okay, the amplitude of vibration in case of support motion depends on the speed of vehicle and the nature of road surface. I hope you are understanding this. That is speed of vehicle matters a lot, as well as at the same time nature of road surface or road surface irregularities also contributes a lot. So the vibration measuring instruments are based on this concept. Okay, so let us assume one system. Here we have shown a mass. Suppose this is a chassis. This mass is the mass of the engine as well as the total assembly of the vehicle, and or we can and here we have the shock absorber. Okay, and this is what the support. Okay, this is our, we can say, the wheel. Okay, so this is mathematical representation of this system. Okay, this is wheel, these are the wheels which are also getting excitation from the bottom surface where they have landed. This is what the shock absorber, it is having combination of spring as well as we can say the damper, and this is a chassis. So this chassis, because of the engine we can say engine input, this gets displaced in the downward direction by amount x, suppose, and this base, these are wheels, because of the road surface get the excitation and get displaced by amount y. So the total deflection might be x minus y or sometimes x plus y, that is depends upon the nature. Okay, but this y we will assume as a exciting force, or we can say periodic force supplied to the wheels, and have the value y is equals to b sine omega t. So in the displaced position, the free body diagram for this case can be drawn like this: m into x double dot, this is the inertia force, as right now we are considering the support motion or displacement due to support. So that's why the directions are like this m into x double dot is which is the inertia force of the system, and is m into x double dot Then this is the spring force, which is equal to k into x minus y. This is the damping force, which is equal to c into x dot minus y dot. With this we will try to solve this equation. In such cases, the support or base is considered to be excited by a sinusoidal motion, which is equal to y is equals to b into sine omega t. The analysis of force vibration due to excitation of support can be done by considering either absolute amplitude method or relative amplitude method. And we have to consider the respect to the mass or support, we can say. So first case we will discuss, that is absolute motion. Absolute motion of a mass means its motion with respect to the coordinate system attached to the earth. The absolute displacement of support is y is equals to b sine omega t. Here in this case, the absolute displacement we will consider as y is equals to b sine omega t, and the absolute displacement of mass from its equilibrium position is x, that is the chassis displacement. The displacement of mass m relative to the support is z, suppose. Then the net elongation of the spring is x minus y, and the relative motion between the two ends of the damper is x dot minus y dot. Then z is equals to x minus y and z dot is equals to x dot minus y dot. The equation of motion with these terms can be written as m into x double dot plus c into x dot minus y dot plus k into x minus y is equals to 0. Now we will rearrange this equation and can be written as m into x double dot plus c into x dot plus k into x is equals to c into y plus k into y. Let us call this equation as equation number 1. The support is subjected to harmonic vibration. Otherwise, it is none of use for us, because we are considering it as a force vibratory case. So when we have to see, when we have to discuss about the vibration, that time we have to assume that whatever the excitation force is acting on the system must be a harmonic or periodic one. Then and then only we can solve them as a linear equations. Okay, so that's why here the word is harmonic vibration, and this can be given as y is equals to b into sine omega t. Substituting value of y in above equation 1, we get m into x double dot plus c into x dot plus k into x is equals to c into b into omega cos omega t plus k into b sine omega t. If you remember this equation, what is that equation is c into y dot, so we have to carry out the derivative of y. So we could write the equation, we will get the equation like this: c into b into omega cos omega t plus k into b sine omega t. So b, we will rearrange the terms, we will take the b common from both these terms. We could write the equation like this: b in the bracket c into omega cos omega t plus k into sine omega t. B into, again rearrange the equation, k into sine omega t plus c into omega cos omega t. Now let us divide and multiply this side of equation by square root of k square plus c square omega square. So we will write the equation like this: k upon square root of k square plus c square omega square into sine omega t plus c into omega upon square root of k square plus c square omega square into cos omega t. Okay, then we could write the equation as b into square root of k square plus c square omega square in the bracket cos alpha into sine omega t plus sine alpha into cos omega t. So from where this cos alpha and sine alpha comes into picture? So here is the reason for that. Let us say, if you remember the phase angle vector diagram of the forces came in the picture when we see the force vibration. That time we have seen such type of diagram, that along one side of the triangle we have the spring force, then this is what the damping force, and this is what the force which is applied on the system. So we came across the triangle like this. Let us say this angle is alpha. Then from this triangle we could write cos alpha is nothing but k upon square root of k square plus c square omega square. So from this triangle we will write for this term as cos alpha, and this term which is c into omega upon square root of k square plus c square omega square. If you look into this picture, or we can say this triangle, you can easily understand. So we can get the equation like this: b into square root of k square plus c square omega square in the brackets cos alpha into sin omega t plus sin alpha into cos omega t. Ultimately the equation 1 can be written as this equation we can write like this: m into x double dot plus c into x dot plus k into x is equals to b into square root of k square plus c square omega square into sin omega t plus alpha. Let us call this equation as equation number 2. Now from the same triangle we could write for tan alpha or tan as tan alpha is equals to c omega upon k. Okay, where alpha is equals to tan inverse of c omega upon k. Alpha is equals to, but if you remember one, we can say the value for c into omega upon k when we have discussed the damped vibrations in for our unit number 1, that time for this quantity c into omega upon k we got the value as 2 xi into omega upon omega, and after so many iterations we can say some formulations we could get the, by some operations we can get the value for c omega upon k as 2 xi into omega upon omega n. So we could write, we will give the number to this equation as equation 3. Now steady state solution or particular solution is given as xp is equals to x is equals to a sine omega t plus alpha minus phi. Comparing equation 2 with the equation of motion for force vibration, that is m into x double dot plus c into x dot plus k into x is equals to f into sine omega t minus phi. This is what the equation of motion for force vibration. If we compare this equation with the equation 2 that we have just arrived at, we can write for f is equals to b into square root of k square in plus c square omega square. Let us call it as equation number 4. Now as we know that for force vibration the amplitude can be given as a is equals to f upon k upon square root of 1 minus omega upon omega in bracket square, then square of this bracket plus 2 xi into omega upon omega n bracket square, then close the bracket. Okay, so for this f just we have got from equation 4 as b into square root of k square plus c square omega square. This is the value of f in the case of support motion. Therefore we could write the amplitude of force vibration due to support motion is equals to a is equals to b into square root of k square plus c square omega square upon k upon square root of 1 minus omega upon omega n bracket square, then bracket square plus 2 xi omega upon omega n bracket square. Therefore we could write, we will rearrange this equation: a upon b is equals to, now this k which is in numerator can be given inside the square root, then we could write the equation as square root of k square upon k square plus c square omega square upon k square upon this quantity remains as it is in the numerator, sorry, in the denominator. Now we could rearrange and we get the equation like this: a by b is equals to in the square root of 1 plus 2 xi omega upon omega n, as we have c omega upon k is equals to 2 xi omega upon omega n. So for that we could write like this: 2 xi into omega upon omega n bracket square upon square root of 1 minus omega upon omega n bracket square, then bracket square plus 2 xi omega upon omega n bracket square. Let us call this equation as equation number 5. The ratio A by B is called the displacement transmissibility, which is the ratio of amplitude of the body to the amplitude of the support. I hope you are understanding this. A is what? The amplitude of the body, that is chassis, and B is what? Amplitude of the support. As a tan alpha is equals to c into omega, just we have seen c into omega upon k. So alpha is equals to tan inverse of c omega upon k. We just have solved this equation, so we could write tan inverse in of 2 xi omega upon omega n. And for the phase angle of the force vibration, phi is what we have: phi is equals to tan inverse of 2 xi into omega upon omega n upon 1 minus omega upon omega n square. So the phase angle when we consider the support motion can be given as phi minus alpha. Phi is the phase angle for without considering the support motion. Alpha is another, or we can say again it is been added or again can be subtracted from the total phase angle, and the total phase angle in case of vibrations, force vibration due to support motion can be written as phi minus alpha is equals to, keep the value of phi as well as alpha, we get the equation like this. Let us call this equation as equation number 6. Now the another case to solve the force vibration due to support motion, another way, so we have to consider the relative motion. In the previous article we have considered the absolute motion, and in that we have assumed that z is the relative displacement of the mass with respect to the support, so it can be written as z is equals to x minus y. Similarly, z dot is equals to x dot minus y dot, and z double dot is equals to x double dot minus y double dot. Let us call it as a. Substituting this in the above equation, we get m into x dot x double dot plus c into x double dot c into x dot plus k into x is equals to c into y dot plus k into y. In this equation we will put the values of a, so we get the equation like this: m into x double dot plus c into x dot minus y dot plus k into x minus y is equals to 0. So m into, so x double dot is what we have, z dot plus y double dot, okay, z double dot plus y double dot plus c into z dot plus k into z is equals to 0. Therefore we could get the equation like this: m into z double dot plus c into z dot plus k into z is equals to minus m into y double dot. Okay, so as we have y is equals to b sine omega t, just we have seen in the previous case, or in the figure we have y is equals to b sine omega t. Now we will keep this value over here and we will resolve the we will resolve this equation. So m into z double dot plus c into z dot plus k into z is equals to b into omega square sine omega t. This equation is known as relative equation of motion, and it is of the same form as equation m into x double dot plus c into x dot plus k into x is equals to m0 into e omega square sine omega t. Let us assume that the steady state relative amplitude z lags the excitation by angle alpha. So we get z is equals to z into sine omega t minus alpha. Therefore the steady state amplitude can be given as z is equals to m into omega square into b upon k upon this square root 1 in the bracket 1 minus omega upon omega n square, square the bracket, plus 2 xi omega upon omega n square, this total quantity is in square root, is equals to, again we will rearrange the terms, m by k is what we have, omega n 1 upon omega n, so here we have the square of it, so we could write b into omega upon omega n square upon square root of 1 minus omega upon omega n square bracket square plus 2 xi omega upon omega n square, and with the phase angle alpha is equals to tan inverse of 2 xi omega upon omega n upon 1 minus omega upon omega n square. So this way we get the phase angle as well as the amplitude when we consider the relative amplitude of the vibration when support motion is there. So both the formulas are different, so we have to remember these formulas, and depending upon the question they have asked, you have to use the formulas, respective formulas, for solving the numericals. Thank you.